This is a section on applications of linear equations, but we are going to focus just on mixture problems, which you had in the course prior to this, but we're going to go back and revisit it because it's one of the tested learning outcomes in college algebra, so it's real important that you get this. If you look at the top of your notes, you'll see the steps for solving the applied problems. I'm not going to read those to you, but we're going to go through this, and I'm going to show you two different ways to do mixture problems. The first way is using one variable. That's probably the first way you learned. The second way is using a system of equations, and they're very related, but I want you to see how they fit together. So let's look at example 1. And this is just using one variable. All right. Example 1 says, Candy has $70,000 to invest and requires an overall rate of return of 9%. She can invest in a safe government-insured certificate of deposit, but it only pays 8%. To obtain 9%, she agrees to invest some of her money in non-insured corporate bonds paying 12%. How much should be placed in each investment to achieve her goal? And I know what you're thinking. It's like there's just too many words and too many numbers and you don't know how to begin. So we know that when you're using one variable, or when you're using two even, there's two things we're talking about here. So we're talking about investing some at 8% and investing some at 12%. And that's to get an end result of a 9% overall rate of return. So we're going to say, state our variable, let x equal the amount that she's going to invest at 8%. Now this next let statement is the one that causes students trouble. And that is, we have to have a way of showing the amount that she's going to invest in 12%. Well, you have to think about it that she has $70,000 total, so if some of it, X, is going to be invested at 8%, then the rest of it's going to be invested at 12%, and the rest of it is represented by $70,000 minus the amount she already used. That'll give you the rest. So you just have to get used to that idea. Now, as is true with all mixture problems, we have an amount times a percent or a cost, depending on the problem, plus a second amount at its percent will always equal the total amount at its percent or its cost. So in this case, it is percents. And we also know that we can't use percents as percents. We have to change them to decimals, so that's what those two would be. So the amount we have at 8% would be represented by 0.08, that's the percent, times its amount, x, plus 0.12, that's the percent, times its amount, which is right here, 70,000 minus x, equals the total amount, which we know is 70,000, and its percent that she wants to end up with is 0.09. So we've got amount times percent plus amount times percent equals total amount times its percent. I just wrote these in different order so it was more standard. Let's go ahead and distribute 0.08x, 0.12 times 70,000, do that on a calculator and you get 8,400. Distribute again, minus 0.12x equals, multiply this side out and you get 6,300. Combine like terms, 0.08 minus 0.12 is negative 0.04x plus 8,400 equals 6,300. Subtract to get numbers on the other side. We end up with negative 0.04x equals negative 2,100. Divide by the coefficient, negative 0.04. And we end up with x equals 52,500. Now we're going to go back to our let statement. What was x? It was the amount at 8%. So it's $52,500 at 8%. And now the 70,000 minus x, which is right here, that's the other amount, is going to give us the money she's got left over. That's going to be equal to 17,500 at 12%. So there it is done with one variable. All right, let's do another one with one variable, and then I'm going to show you how you could do it with two variables. Number 2, the manager of a Starbucks store decides to experiment with a new blend of coffee. She will mix some B-grade Colombian coffee that sells for $5 per pound with some A-grade Arabica coffee that sells for $10 per pound, and she wants to get 100 pounds of this new blend. She's going to sell that for $7 per pound. So what we want to know is how many pounds of the B-grade Colombian and the A-grade Arabica coffees are required. So again, we're going to say, let A equal the amount of Arabica. Now, altogether, she has 100 pounds that she wants. So once you know what that amount of the Arabica is, 100 minus A is going to equal the amount of the Colombian, because it's going to be the rest of it. And that's how you've got to think about it. And this is really the key to these problems. So again, this time we have an amount times its cost plus an amount times its cost equals the total amount times its cost. The only difference between this one and the last one is we have cost instead of percent. So again, I'm going to reverse the order here. So it's going to be $10 plus or times the Arabica plus the Colombian. Its amount is 100 minus A, and it costs $5. I'm only putting it in the front instead of behind it because it's easier to distribute that way. Equals the total amount is 100 times what she's going to charge for the total is 7. So you've got 10A plus distribute, 500 minus 5A equals 700. Combine like terms, 10A minus 5A is 5A plus 500 equals 700. Subtract your 500, and we have 5A equals 200. Divide by 5, and we get A equals 40 pounds. I'm going to go up here. That is the Arabica. So 40 pounds of Arabica, and then the rest of it, which is 100 minus A, that's 60 pounds of Colombian. That one was a little bit easier just because the numbers were easier. And that's how you do mixture problems with one variable. Now look on the back of your notes. I'm going to show you how to do it using two variables. Only I need to do a quick review of systems of equations from the prior class. So if you'll remember, there were two ways of solving a system of equations. A system is just is two sets of equations. So we've got the elimination method. And I have the steps there. Get both the equations in standard form, multiply or divide each side of either or both equations in order to eliminate a variable, combine the equations through addition, and then you substitute back to get the second. So let's take a look at one of those. I'm going to review these, and then we're going to go back and apply it to our mixture problems. So we've got this system, 2x plus 3y equals 1, and negative x plus y equals negative 3. To solve by elimination, I have to get one of my variables, either x's or the y's, with the same coefficient but opposite signs. So I can easily see here, if I multiply the second equation, everything in it, by 2, then I would have a 2x on the top and a negative 2x on bottom. That's what we want. So we're going to have 2x plus 3y equals 1. I didn't change that equation. Sometimes you do. Sometimes you have to multiply both of them. The second one, if I multiply by 2, I get negative 2x plus 2y equals, don't forget to multiply the other side, negative 6. Those x's go away. That was our whole goal. And you have 5y equals negative 5. Divide by 5, and you get y equals negative 1. Now, when it's not a word problem, not an application, and you're solving a system, if you'll remember, what you're looking for is a point of intersection. So I just found the y part of that point. To find the x part, I'm going to substitute back in either of my original equations. I'm just going to do the top one. So 2x plus 3, take out the y, put in the negative 1, equals 1. 2x minus 3 equals 1. Add a 3, and we get 2x equals 4, divide by 2, and you get x equals 2. That goes here. And that tells me that if I graphed those two equations, the place where they would intersect would be at the point 2, negative 1. And again, bear with me, you're going to see how this applies to mixture problems in just a second. Let's look at the other way, substitution, and this is typically the way that we use when we're doing mixture problems with two variables. So, example 4, the steps are to solve one of the equations for either variable, and then you have a substitution equation. You substitute that back into the remaining equation and solve. So, let's do that. We have 2x plus y equals 5, and I've got negative 4x plus 6y equals 12. Actually, this one is set up to probably work more easily with elimination, but I'm going to show it to you with substitution. I notice that right here I have a y that has a 1 for its coefficient. So I'm going to take that equation, 2x plus y equals 5, and I'm going to solve it for y. So I subtracted 2x, and I get y equals 5 minus 2x. That becomes my substitution equation. And where am I going to substitute it? I'm going to take what y is equal, and I'm going to put it right here in the other one, in the y place. So that would give me negative 4x plus 6, take out the y, put in what it's equal to, 5 minus 2x equals 12. Negative 4x plus, distribute both, equals 12. Combine like terms, negative 16x plus 30 equals 12. Subtract your 30. Negative 16x equals negative 18. Divide by the coefficient, and you get x equals, if you simplify that by dividing by 2, negative over negative is positive, and we end up with 9/8. That would have been the first part of the point of intersection. Now, how do I get y? This is why I like the substitution method. Once I have x, I have this handy-dandy little equation to get y. It says y is 5 minus 2 times x. So y equals 5 over 1 minus 2 over 1 times 9 over 8. Cross cancel. Y equals 5 over 1 minus 9 fourths. Common denominator is 4. Y equals 20 fourths minus 9 fourths, which is 11 fourths. And I have the other piece of my point of intersection. This is the way we're going to use for the mixture problem, only the numbers won't be quite so difficult to deal with. So let's go back to the same example, example 2. I have it written on here again as example 5. It's this, I'm not going to read it again, about the coffee. So what we're going to do is we're going to rework the problem using two variables. So I'm going to say, let A equal the amount of Arabica. Now, if you'll look back in your notes, you'll see that's exactly how we started it with one variable. But rather than saying let 100 minus A equal the Colombian, I'm going to use C. Let's let C equal the amount of Colombian coffee. Now what we're going to do, rather than just writing one equation, that's amount times cost plus amount times cost equals total amount times total cost, we're going to write two equations. The first equation is what I call the amount equation, and what it says is the amount of Arabica plus the amount of Colombian has to equal 100 pounds, because the problem said so. The second one is the value equation, and it has the cost along with it. So Arabica at $10 plus Colombian at $5 is going to give you the blend, 100 pounds of it, at $7. So now what I have is I have two equations. Let's simplify this one. 10A plus 5C equals 700. So I'm going to use the substitution method, and I'm going to take this equation and I'm going to solve it for C. Well, C would equal, subtract an A from both sides, 100 minus A. Now notice, that's exactly what we did when we did it with one variable. We just jumped right to this without showing that amount equation first. So they're really the same thing. So I'm going to take this substitution equation and I'm going to substitute that C part right there. So I would have 10A plus 5 times 100 minus A equals 700. And if you'll go back in your notes, you'll see this is exactly what we had written. We just, like I said, skipped this part when we did it with one equation. But for some people, it's easier to think of it like this and actually write that amount equation out first. So 10A, you know what the answer is going to be because we've already done this, equals 700. We ended up with 5A equals 200, subtract a 500 from both sides, divide by 5, and you get the same exact answer we got the first time. That the amount of Arabica is 40 pounds, so the amount of Colombian is 60 pounds. It's just a matter of how you think about it. Let's do one more using two variables and the substitution method, or the elimination if you prefer. A movie theater sells tickets for $8 each, with seniors receiving a discount of $2. One evening, the theater sold 525 tickets and took in $35.80 in revenue. How many of each type were sold? So there's two types here. So we're going to say, let X equal the number of $8 tickets sold, and Y is going to be the number of, now be careful, it's not $2 tickets, it was a $2 discount. So they are $6 tickets that were sold. So let's write our two equations. The amount equation would be the number of tickets, X plus Y equals 525, and then the value equation has the prices with them. So X cost $8, Y costs $6, and we don't need to multiply 525 times some number because we already know how much money was taken in. So this is the value that was taken in was $35.80. The right-hand side was already done for you. I am going to solve this one and have it be my substitution equation by subtracting an X from both sides, and I get Y equals 525 minus X. Okay, that's going to be my substitution equation, and it's going to go in for the Y right there. So 8X plus 6 times 525 minus X equals 3580. 8X plus, go ahead and multiply, you get 3,150 minus 6X equals 3,580. Combine like terms, 2X plus 3150 equals 3580. Subtract the 3,150 from both sides. You get 2X equals 430. Divide by 2, and we get X equals 215. And what was that? Go back to your let statements and you will see X was 215 tickets, I'm going to abbreviate there, at $8. And since there was a total of 525, I have this, again, very handy equation to find Y. So Y equals 525 minus 215, and Y equals 310. So 310 tickets at $6. Personally, I think mixture problems are easier with two variables. That's just my opinion. And you will see homework listed at the bottom of your notes page, so make sure you practice those. You're going to have one of these on your final exam.